Hello. And thanks for watching this presentation. We will try here to get a deeper look into the Mandelbrot value space. For this purpose we use the concept of Mandelbrot surfaces which we introduced in the presentation about the three-dimensional Mandelbrot forest. First, recall the definition of the Mandelbrot surface sequence. Some simple calculations show that the surface function results to be a polynomial surface of degree 2 to the power of n plus 1 over the real plane. Let's say it's a sequence of things like, for example, this. What happens is that the real Mandelbrot polynomial sequence is a little bit more complex, and it gives us a good idea why such a simple function as the Mandelbrot function generates a such sophisticated object as it is the Mandelbrot value space. Here are the first four members of the Mandelbrot polynomial sequence. For the index 1 we get with the corresponding surface. The next one corresponds to index 1. And it generates this surface. Now we come just to the polynomial with index 2. The generated surface is. The next one corresponds to index 3. And the generated surface is. The last one we show corresponds to index 4. And the corresponding surface is this. We see that the most important characteristic of the Mandelbrot object is not the base function but the concept of iterative function. For this reason, when we substitute the original base function by another nonlinear function, as it was done in a lot of investigations, the generated value space is different and the generated shapes are different, but the resulting object shows similar complexity as the original one. As an example, we substitute the original Mandelbrot iteration rules by the following rules. With this substitution we get also a sequence of surface polynomials, and this sequence also is of exponentially growing complexity. The corresponding shape images show a similar amount of complex geometric structures, including self-similarity, fluttering, etc. The only things what this sequence does not produce are symmetric geometric structures as the original Mandelbrot sequence does. For index 1 we get. And for index 2. For index 3. With the index 3 surface. And finally for index 4. With the index 4 surface. For the peculiar shape of the value space of this sequence we call it the asteroid polynomials. More details you find in our presentation with the same title. Before showing the central videos of this publication, let us see how the polynomial surface concept relates to the traditional escape value concept. As we see, the escape value concept throws away all detailed geometric information of the corresponding iteration step, whilst the surface concept brings out a big part of this information. Look the following comparative images of escape value layer 21 at zoom level 1200. Now we come to the question of how to visualize the generated Mandelbrot surfaces. Basically we have two possibilities. Representation as a flat contour map. Representation as a 3D spatial object. To improve the clarity of the generated images in both cases we use an imaginary waterfront height to separate low values from high values of our polynomial surfaces. As usual in contour maps, the lower ocean part is painted with colors in the blue range whilst the landmass part is painted with colors in the brown range. To improve just more the readability of the images, the shoreline is marked with a tiny dark blue underwater line followed by a brighter red line just below the waterfront height. Above the waterfront height comes first a bright yellow line followed by a tiny green line. To visualize the enormous height values which landmass pixels can achieve, we use for pixels with height values from a certain limit upwards colors in the white to beige range. Finally, in 3D spatial object representations, the extremely big height values and also the extreme height distances of pixels requires another coloring concept. For example, for a pixel and his neighbor, the surface heights may be separated by a factor higher than E305. This effect leads to images where the geometric structure vanishes as a result of the lack of pixels to paint. For this reason, extremely height values are painted with random colors. In videos, this makes these points showing a type of flickering as in the outbreak of a volcano, expulsing surface pixels to infinity. The following video shows the first Mandelbrot polynomials for index 1 to 15, with zoom sequence between 17 and 1200, and flying a curve from the outside of the Mandelbrot figure to the interior, passing the main gate and entering into the highway canyon which leads to the highway junction area. Take in mind that the first four of these polynomials we saw just above when we presented the polynomial expressions in the Mandelbrot case. As the range of the surface's heights in the case of this video results fairly moderate, the random color concept is not used here. Let us now show some short video clips to compare both representation methods. The parameters of both clips are the followings. First come the clip with a flat contour map representation. After the flat contour map representation comes now the clip with a 3D spatial object representation. Perhaps you just noticed that in our video representations we are applying a certain type of slow motion camera. We do this to give you a better chance to capture what really happens in the Mandelbrot polynomial sequence. This slow motion camera is nothing else than moving from one polynomial to the next one along a straight line in the underlying polynomial space. When we visualize polynomials of higher index, for example polynomials with index higher than 500 and also higher zoom levels, for example higher than E12, then the 3D spatial object representation normally loses his interesting character. This is due to the fact that as higher the zoom level and the surface index are, the surfaces become more and more flat, so that a three-dimensional representations does not contribute nothing to the visible geometric structure of this surfaces. It is also worth to mention that at zoom levels from E14 upwards we come to the end of the double precision universe which normal home PCs offer. In the last part of this presentation we'll try to give a clear visualization of how the perforation process of the Mandelbrot polynomials work. First, a video to see how the characteristic Mandelbrot caterpillars are devouring step by step the surface, and when the consumed pixels are digested they expulse them to infinity. This video is a little bit longer because it shows as caterpillars in the polynomial sequence between index 249 and 440 transform a nearly complete closed surface into a set of almost separated islands. Finally, we will show how the Mandelbrot caterpillars look in a three-dimensional view. In this representation environment they look like volcanoes that go forward step by step, repeating forever an elevation of the surface heights followed by a similar decrease of this heights. During each one of these cycles a small portion of the surface pixels is blown away to infinity. With the concepts and utilities now developed, we can get out a lot of videos at the many different and amazing points of the Mandelbrot object. Also with different view angles and different zoom levels. Some of these videos will be presented in future publications. Here are some trailers of these videos.